right, so this is where we stopped, and we were talking about what are the strongest reconstruction type attacks, and I think we ended on a note where we believe these randomly constructed sequences are strong, but they're not the strongest. And so there's an open question for the community to look at different ways in which you could construct strong reconstruction attacks. And there are some mathematical questions in that direction of how should we set up an optimization problem to find those training sequences that are as strong as possible. But I want to move on to something that's related, slightly different, which is the following question, which is, okay, we've done this type of an auditing via these reconstruction attacks. Is that the best way or the strongest way in which we could do privacy auditing? Or is there an even better way? Does anyone have an answer? So we've so far just seen reconstruction attacks. I plug in a prefix, I try to see how well I can reconstruct a suffix. Maybe 50 tokens in, see how well you can reconstruct 10 tokens out.
Go the other way, go backwards along it. Given an output, can you determine what the prompt was or what the, I guess, before it came?
That's one thing we can do, yes. Anything that's even stronger, but maybe in that direction?
You do things like augmenting the data set, which means that probably permeating the text so that it has this variance that could probably make a larger set of inputs to minimize the privacy.
That's also a feasible direction, and it's related. Any other ideas? Yeah.
Train an adversarial model to come up with high-performance strings.
Okay, that's also very nice. I like the adversarial model part of it. We'll see that. Other predictions?
Maybe randomize the suffix and then keep the prefix the same.
Yep, but that falls in the reconstruction. But yes, I agree. All these answers are actually correct. There's a spectrum of attacks that we can conduct. What we focused on is this end of the spectrum, which is, what the adversary is interested in doing here is to what extent you can generate text exactly or, partially. So we've looked at these two blocks. Generate training text that belongs to one user or a few users, either exactly or with some errors, so like partially. That was the edit distance that we saw. But we can do something that's, in between, learn properties about users. Just properties. I don't want to complete sequences. Learn that Peter has a property A that's unique to him. So rather than complete 10 tokens have a lot of bits of information. Each token is about 8 bits, 1 byte. So 10 tokens, that's 80 bits of information. So this adversary here is trying to learn 80 bits of information. Maybe I want to learn only 1 bit. How about that? I just want to learn one tiny bit. Was Peter in that training set? Yes or no? Or maybe 1 bit about Peter. Is Peter part of group A or group B? So we can push these attacks all the way down to binary inferences. And those are only like one single bit of information about a user. It's a unique bit, but it is 1 bit. So you can see how as we go from left to right, the attack is getting stronger because the task that the attacker is conducting becomes easier. So here you have to learn 80 bits, 10 tokens. All the way on the other end, you're only learning 1 bit. So it should be an easier task for the adversary to do, to learn 1 bit of information. And we are arguing here is that if you really want to be a privacy purist, you want to protect against the learning of any single bit. And there's, again, a data processing inequality at play here. If you've seen data processing inequalities. If you cannot construct 1 bit reliably, then there's no way you can reconstruct 80 bits reliably. If the easier task is already hard, then the harder task is going to be even harder. So that's kind of how you should think about it. If I can block leakages of unique 1 bit of information about a user, I can certainly block 10 bits or 8 bits or 80 bits. So hopefully this is intuitive, and this is very clean because it gives rise to this kind of an attack. So it's a little more complex, but it's actually a lot more meaningful, and this is where we start going into the hypothesis testing for those who have seen hypothesis testing, but I'm going to explain it all. So here's a hypothetical scenario. I have 2 training sets. They are exactly the same, except for 1 individual user. In one of them, Alice spent her vacation in Italy. In the other one, Alice spent her vacation in the Faroe Islands. So it's like, two identical worlds except for this 1 bit of information. Location A versus location B. And in this world, we only have 2 locations. Let's say you only can vacation in these 2 places. It's very, hypothetical. So here's what we're going to do. We're going to flip a coin, let's say unbiased coin, pick one of the 2, train the model however you want. In this case, I'm going to focus on fine-tuning, but it could be training from scratch. It doesn't matter. You get a model after training. You're going to present this model to an adversary. So I like this adversarial idea. And the adversary has access to the model. You could give the adversary access to the full model, all the parameters of the model, or outputs from the model. And the adversary has to guess. It's a binary hypothesis test. It's 1 bit of information. Was that model trained on the upper data set, or was it trained on the lower data set? That's it. That's all the adversary cares about. We're not trying to complete sequences. We're not trying to get 10 tokens right, those suffixes, or half of them right, or a few of them right. All we're trying to do here, did you train on the upper one or the lower one? Because if I know it's the upper one, then I know that Alice spent her vacation in Italy. And if it's in the lower one, I know that Alice spent her vacation in the Faroe Islands. So I know that property of Alice. Okay? So this is how we're taking these attacks into an extreme. And in order for us to conduct these attacks, the adversary has to compute a metric, a statistic, that it's going to use in performing this attack. So you need to compute a quantity, and then you look at that quantity, you analyze its distribution, you say, okay, if it's very small, then I'm going to assume it's the upper data set. If it's very large, I'm going to assume it's the lower data set. So what is that quantity? I'm showing it on this slide. What you're going to do is you're going to take, in this situation, the prefix, which is Alice spent her vacation in. That's a common prefix between the upper and the lower data set. And you're going to take the trained model, this fine-tuned model, and you're going to compute the likelihood of seeing a given suffix given that prefix. So we can compute the likelihood of Italy given Alice spent her vacation in. That is the prompt. Again, these models are generative models. They are conditioned on a prompt. They generate an output. So you can compute the likelihoods of the outputs. And you're going to normalize it by the probability of seeing the same suffix given the same prefix from the pre-trained model. So before you've even done any fine-tuning. And this gives you this calibrated test statistic. We need that denominator because there are a lot of sequences that are easy to predict, regardless of whether or not you've fine-tuned. These are things that are present in the fine-tuning data set, but they could have easily been present in the pre-training data set. We don't want to over-index on these things. So you need to calibrate this quantity properly to avoid having a lot of false positives. But once you get that test statistic, you could compute it for 2 different suffixes. You could compute it for Italy as the suffix, and you could compute it for the Faroe Islands as a suffix. And if the Italy metric is much, much higher than the Faroe Islands, that means that it's quite likely that the model, during its training, has seen Alice spent her vacation in Italy than it has seen Alice has spent her vacation in the Faroe Islands. So again, this quantity that I'm showing up there, you computed for the upper data set and the lower data set. And all you have to do is just replace that suffix. You can instantiate it either with Italy or the Faroe Islands for the same prefix, Alice spent her vacation in. And you can compare these two quantities to each other. And if the Italy quantity is much higher than the Faroe Islands, you deduce, oh, it must have been the upper data set. And if the Faroe Islands quantity is much larger than Italy, then you deduce that it was the Faroe Islands. So it's very simple, very basic, very intuitive. There are other ways of computing this test statistic. Notice that I'm just using the likelihoods of the model. I'm not using the parameters of the model. If the adversary were able to tap on the parameters of the model, you might have computed a more sophisticated test statistic. You could have seen the activations of different layers of the model. You could have computed a higher dimensional statistic and then trained a model to take all these d dimensions and do a binary classification. So there's a lot of cool things that you can do here. You can make this adversary operate on d-dimensional test statistics, on one-dimensional, as I'm showing in this case, lots of things. You can normalize. It's an open area of research. But I'm going to keep it simple for this talk. And with this simple one, we can do a lot, in fact. So here's what I'm going to do. I'm going to take the data set. I'm going to add those canary users that I've constructed. And notice here that even though these are all hypothetical users with random generated data, I now have a held out data set. So remember when we did the reconstruction attacks, I said we don't need the held out for the random, because the model, there's no way the model could reconstruct random data. It's just impossible. If it has not seen that random data, there's no way you could reconstruct it. You could verify that through an experiment. But here I need it, and I need it for a reason. In a second, I'll ask you the question to see if you can guess it. But let me show you what we're doing first so that you have enough of what you need to guess the answer. So I'll combine the data with the random held in canaries. I'll run the fine-tuning process. I'll obtain the model. I will take these two things, put them together, shuffle them, give the adversary all the canary users and the model, and ask it for each one of those canaries, can it determine whether it was in the held in set or in the held out set. So for each canary user, you make a binary inference, a simple binary inference, 1 bit. Was it held in or held out? So in this case, I have 6. In practice, we'll have a lot more, in the thousands, tens of thousands of them. And we'll get 6 decisions. So I'll run this adversary 6 times. For each time, I will ask it, was it in the held in or in the held out? And I'll use the test statistic that I showed you on the previous slide. Yep.
Could you go back?
Yes.
Wouldn't you require these probabilities to be calibrated in something?
Yeah, so the denominator here is for calibration.
I see.
Without this denominator,
This is untenable, right? Because
Yep.
you have
Yep.
probabilities.
yeah, you would have a lot of false positives.
Exactly.
Because some of these sequences are easy to generate. Now notice if I do random canaries, not natural text like I'm showing you here, you don't need this denominator. Because the pre-trained model is likely not going to know how to get the suffix out of the prefix. So it's not always very necessary, but for natural data, it would be important to have that denominator for calibration. Okay, so there are some subtleties, and if you're not fully tuned to those subtleties, that's okay. The big picture is what matters most here. I don't want you to worry about the details. We can discuss them even offline if that matters. But just keep the big picture in mind. What I'm going to do is I'm going to create 2 classes of users, and I'm going to use random data for them. half of those users are going to be plugged into the training process, half of them are outside the training process. And I'll train, I'll get the model, I'll give the adversary the combined set of held in and held out. I'm not going to tell the adversary which ones were in versus out. I'm going to use this adversary. The adversary will have access to the model, and it has to decide which one of these was in versus out. So binary inferences. Now, because this is a hypothesis test, for those of you who have seen hypothesis testing before, you know that in hypothesis testing, the way we measure the performance of a decision rule, in this case an adversary, is via two quantities. There's something called false positive rates and true positive rates. Okay? You can look at it false negatives versus false positives, so on and so forth, but I'm going to keep it simple. So what are the false positives? False positives are the users that are in the held out that the adversary labeled as held in. So they're not held in, but the adversary thought that they are held in. That's why we call them false positives. And then the true positives are the users that were indeed held in, and the adversary labeled them as held in. Those are the actual true positives. Ideally, what the adversary wants, it wants to get a high true positive. You want the true positives to be as close to 100% as possible at very low false positives. If you can get to such operating point, extremely low false positive rate, at very high true positive rate, then you have a perfect adversary. You're leaking that one bit reliably. And we're not over leaking that one bit. Because again, if all I cared about is getting the true positive rate to 100%, the adversary will always say, held in, held in. Show it anything, regardless of what you show it, it's always going to decide held in, held in. That would have a high true positive rate, but it would have a high false positive rate. And that's not good. So we want the adversary to be smart enough to say held in for those that were indeed in, and to say held out for those that were out. So to have low false positive, at the same time high true positive. Okay? And usually we look at these things called the ROC curve, the receiver operating characteristic curve. The terminology comes from World War. People were studying these things for radars, detecting planes and missiles and whatnot. They're still relevant today, unfortunately. But, that's where the terminology comes in. So let's actually see, back to our Gemini model and our production data set, now on this test, how well we can do. So it turns out that if each user has only one example, this is looking decent. Actually, not that decent in many ways, because you get a very low true positive rate at a very low false positive rate. So the attacker is not doing super duper well. If you want it to have a low false positive rate, it's not going to have a good true positive rate. So the leakage here is low. So the attacker is not capable of solving this problem really well, because its true positive rate is only 1%. It's still, I argue, from a privacy perspective, 1% of the time, you're labeling those users correctly, there's some privacy leakage. To me, it should be like super duper low, close to zero, that type of low, cryptographically small. But 1%, let's assume, is good enough for this discussion. But notice what happens when we allow each user to have that example 39 times, because we expect that users will have multiple training examples that could be very similar. Those are my training examples, so they capture my style, my preferences, my properties. Look at what happens. We can get a true positive rate of 99.9% at a false positive rate of 0.1%. This is the perfect adversary. And I'm not using any sophisticated adversary. I'm using this one-dimensional test score. I'm not using a neural network for the adversary. I'm not doing adversarial training of nothing. Simple. Basic. And adversary can actually guess things correctly at a true positive rate of 99.9%. So we thought there was a problem with reconstruction attacks. Turns out there's a really big problem when you look at it from the lens of membership inference attacks, or these kinds of user inference attacks, however you want to call them. Yeah.
Is that where the 39 comes from?
No, the 39 comes from somewhere else. Still not that. I mean, I could have used 40 here. I could have used 30 here. It would have been the same. But yes, in a bit.
So I'm sort of thinking the take home from this then is you're able to kind of identify unusual individuals with very, very high accuracy.
Right.
But somebody who's more kind of part of the crowd, actually they're more on the right-hand side.
Ish. So I should have, and I'm sorry I didn't put this slide. I should have shown you the performance of these attacks on real users, because I used Canary users, random users. I should have shown you, because we can do the same thing, by the way, on held in and held out real users. I did held in and held out Canary here. And you would have seen that it would have not been 99.9, but it would have been high. It would have been like 70-something%, which is quite high. Yeah, but this dimension is important. If users are only allowed to contribute one example to the training, then you can limit that leakage quite considerably. Whereas if users can have a lot more training examples, 39 or something like that, then the leakage is going to be high. So I want to highlight this dimension. Yeah, but there's another dimension of how adversarial the users are, and it changes things a little bit, but not a lot.
So what's a training example? It's more
A sequence, it's basically a sequence of 60 tokens in this case. Just text sequence of 60 tokens.
Sorry, it makes me get a little bit confused, but it's trying to do a binary classification model. So
Yep.
why isn't the worst case true positive rate just 50%, like I'm guessing?
No. You can always trade off. So here, maybe I will use the board for this.
It's chopped in front.
Oh, here. Perfect. So
Is the board
can you see this part of the board? So you can plot true positive rate versus false positive rate, right? And so there's this line, the y equals x line. This is the 50-50, if you want. And the perfect attacker is one that could get a true positive rate of 1 at 0 false positive rate. So if your attacker can do something like that, then it's great. If your attacker is here, that means it's like the worst thing possible.
Yeah, it's just 1 point in the RSC.
Exactly. It's 1 point in the RSC curve. Okay. All right. So there's a big problem. We need to fix it. We can go and use all sorts of heuristics to fix it. We can go and start, like processing the data in weird ways to, remove this issue. And there are people who have used those heuristics. We can go and be like, oh, remove anything that looks like names, remove anything that looks like emails, and try to train and see if this thing persists. But it's always going to persist, because any processing you perform on the data set isn't going to be perfect. There's no such thing as I can reliably pre-process a large data set of all sorts of users in order to make this problem go away forever, for good. And for privacy, my philosophy is you need a provable guarantee. You need something that actually targets these problems theoretically and gives you a guarantee against these classes of attacks. And so this naturally brings me to this notion of user-level differential privacy. And so this is where we're starting to get into like the deepest things, but I'm going to be very slow if you haven't seen. Who of you have seen DP, by the way? Okay, very few, so like 10%-ish. So that's why I'm going to be very slow here. So what is differential privacy? It's going to be designed to target the attacks that I've just shown you exactly. So take two data sets, D and D prime. Assume the only difference between D and D prime is one user. That's it. Let's say in the upper data set, there's no Peter. In the lower data set, there's Peter and all the data of Peter. The query here is going to be some model training algorithm. It's going to be a randomized training algorithm. So maybe use some sort of randomized, noisy stochastic gradient descent to train a model on the data set. And so in the upper diagram, you're going to get a model trained on D. And it's not a deterministic output, it's a randomized output. So we think of it as a distribution over models. And in the lower one, you're going to get a distribution of models, but trained on D prime. Again, D and D prime are exactly the same except for this one user. Think about the attacks that we just saw. What differential privacy says is that these two models, the random objects, they should have distributions that are indistinguishable. If those two distributions were very different from one another, then it should be easy for the adversary that we just saw to distinguish between them. If I give you samples from one versus the other, if I give you an M from D versus from D prime, if those two distributions are very shifted apart, then it should be very easy for the adversary to do that binary inference reliably. But if those two distributions were strongly overlapping, were super duper close to each other, then it's going to confuse the adversary. From just a statistical perspective, two overlapping distributions are very hard to distinguish, regardless of how much compute the adversary has. So even if it has a lot of statistical knowledge, a lot of compute power, infinite compute power, if these two distributions are overlapping, it cannot really distinguish them. So we need a measure of indistinguishability between distributions of models. You can do it in lots of ways. You can use KL divergence. You can use all sorts of F divergences if you've seen them. Differential privacy uses one such divergence, and it's called the infinity divergence, or the max divergence, if you've seen it in your stats or information theory class. And that's what it looks like. Now, I don't want you to get balked by the equation. Honestly, the equation doesn't matter at all. All it's saying is that the distribution on M of t should be very similar to the distribution on M of t prime. And if this equation doesn't make much sense to you, trust me, it didn't make any sense to me the first few times I saw it. I had to see it and see it and see it and see it so that I understand it. So it's totally fine if you're just like, what the heck is that? That was my reaction the first time. But I just want you to trust me on this, and I'll explain it to you in a bit. But there are two parameters that control how close these two distributions are to one another, the epsilon and the delta parameters. One is multiplicative, and the other is additive. That's why we want the additive term to be extremely small. Think delta 10 to the minus 6, 10 to the minus 9, 10 to the minus 10, cryptographically small, that sort of thing. And we want the epsilon to be ideally close to 1 or less than 1. And I'll come back to this and tell you why. Again, maybe this type of divergence doesn't make sense. If it doesn't make sense in your mind, just say KL divergence, or whatever. Plug any divergence between distributions you want. It's okay. Here's the thing about this divergence, why it's so actually pretty. Remember this game that we just played? You have one of two data sets. You toss a coin, you pick one of the data sets, you train. Now I'm emphasizing the randomized algorithm that I'm using. You show the adversary the output the adversary has to guess. And we said that we could measure the performance of the adversary using the true positive rate versus the false positive rate. And we looked at some combos before. Our production data trained without differential privacy at all. We said there's a problem. Well, it turns out differential privacy gives you a formal guarantee on the pair of true positive and false positive rates. If you train with epsilon delta differential privacy, those were the two parameters that I just talked about, it means that the adversary, no matter how strong it is, no matter how computationally powerful it is, it cannot simultaneously achieve a high true positive rate and an arbitrarily low false positive rate. Look at this weird trapezoidal shaped red curve. Notice how when we start approaching a false positive rate close to 0, the maximum achievable true positive rate is very low. You can't go up to 1 as we did before without DP. It says, no, no, no. If you want false positive rates to be small, you've got to pay the price in true positive rates. That's why it's so elegant. It's so relevant to the problem we're trying to solve. So let me give you 2 examples. If you choose epsilon equals 1, which I told you it's a good choice, this is a very small delta, then you get a region like so. It says that the adversary cannot reliably get a high TPR at an arbitrarily low false positive rate. But if you choose an epsilon that's much larger, in this case 3, then the adversary could achieve higher true positive rates at low false positive rates. That region is bigger, at least the theoretical region. And guess what? This guarantee will apply as long as the algorithm, this randomized algorithm, satisfies the property that I showed you on the previous slide. So as long as you satisfy that mathematical condition, you can enforce it, you get this property. Regardless of the adversary can be anything, and regardless of the pair DD prime. You can construct as adversarial pair DD prime as you'd like. You can search for infinity for, worst case pair of DD prime. The distribution of the data can be anything you want. You could have it be monotonic, duotonic, uniform, anything. It does not matter. The adversary can be any compute function with any capacity. This thing will hold. And that's the beauty of differential privacy. It gives you this guarantee regardless of all these things. You don't have to worry about it. You don't have to, oh, what if I missed an adversary class that's feasible in practice? What if I missed a data point that could have appeared in practice? You don't care. It's very worst case. Not only that, it applies even if you reveal to the adversary not just all the parameters of the model, but all the intermediate checkpoints of training. So it applies in a very strong sense. And that's really what I want you to take away from this, and why it's like good at the same time there's going to be a price we're going to have to pay for this thing. It doesn't come for free. It's not just, like we're going to use it and it's going to work right off the box. It's going to introduce a lot of challenges. So let's talk about how we achieve it. And this is the part that's going to get a little technical, but not too technical. So feel free to interrupt me if I say something that doesn't make sense to you. And also, to be quite honest, if you don't get all the points in what I'm going to present in the next 3 slides, that's totally fine. You're still going to enjoy the talk and get a lot of it. So don't get too caught up in the details. This is just like interesting fluff, but not super duper important for this talk. But it will make it a little richer, if you enjoy these things. So there's this notion of a query that we're computing on a data set. And this query can be anything. It could be I'm taking some records and just counting something, or I'm computing averages, or I'm computing gradients on training examples, and I'm averaging those gradients to make a model update. So this query could be anything. Very general. Okay? Any statistical query you can think of. It could be a SQL type query, it could be a model training algorithm. And what we want ideally is a randomized approach where we take the query output and we add to it Gaussian noise centered around 0 with a standard deviation of sigma. I'm assuming everything is scalar. I'll generalize the d dimensions in one slide. But just bear with me a minute here. Just scalar quantities for now. So clearly, I need to add some noise to my training, or in this case, to my query, so that I obtain this differential privacy property. I can't give you the exact deterministic result, because then Q of D and Q of D prime will be different with probability 1. You can easily do this binary inference on them. It would be like deterministic gap between them. I want to fuzz things out. I want to create distributions and overlap these distributions as much as possible. So what do we do now? We will ask ourselves, how do I set this sigma? Do I add a lot of noise? Do I add a little bit of noise? And it turns out that the right quantity to look at, and it will make a lot of sense, is basically this sensitivity function. Again, in a lot of functional analysis, if you've taken math classes, there's the sensitivity of a function or the sensitivity of a query, where basically what you do is you wiggle the inputs a little bit and you see how much does the output change, right? And in this case, what we're doing is we're taking two data sets, D and D prime, and we're looking for all pairs of D prime. What's the absolute difference between Q of D and Q of D prime? In many ways, what we're doing is we're saying, what's the sensitivity of this query to one individual user? If I change that one user arbitrarily, so let's say D does not have Peter, D prime has Peter, for all types of Peter in the world, all possible instantiations of that individual, how much can Q of D and Q of D prime be different? What's the maximum influence that Peter can make on the output of this query? So this is the sensitivity of the query. This is for scalar queries. We're going to see it for d-dimensional queries in a bit. And what we kind of want to do is, so I'll give you some examples of these queries. If it's a count, if this query is just counting, the number of individuals that have COVID-19 in the data set, then I could either have that property or not. So the max I could influence Q is 1. If you take Q of D without me minus Q of D prime with me, the worst case that this thing can change is by 1. If it's like a count query, I'm just counting things. This is a very simple query. And what we want is to set the sigma of the noise, the standard deviation of the noise, such that it's the sensitivity divided by the epsilon that we want to target. Now this makes a lot of sense. The more sensitive the query is, the more we have to add noise. If I can influence the query a lot, I have to add a lot of noise, because I want to mask the influence of any user. And the smaller the epsilon is, again, we said epsilon, we want it to be ideally smaller than 1. We want it to be as small as possible. The higher the sigma. So if you want more protection, stronger guarantee, you have to add more noise. So it's inversely proportional to epsilon. It's very intuitive. It's very simple. And there's a proof for it. I can take this, and I can now prove to you that this recipe satisfies that equation that I presented a few slides ago. I'm not going to show the proof. It's not that important. Hopefully you're going to trust me on that one. How do we generalize this to d dimensions? So now the query can output a vector in d dimensions. Now let's say I'm computing something like gradients. The data set is users with text. I compute gradients. I take the average of the gradients, let's say. So that query is a d-dimensional vector representing the average gradient in a round of training. That's one way to think about it, but it could be others, and I'll show you some examples. So now I have to add noise, but that noise is going to be d-dimensional noise. And the most basic noise that we can add here is one where it's IID Gaussian noise. So the covariance matrix is the identity matrix. It turns out that colored Gaussian is actually also quite helpful. We'll get to it a little bit towards the end, but not now. For now, it's simple. We're going to keep it IID noise. Now we compute the sensitivity a little differently. Instead of it being a scalar, we use the L2 norm between Q of D and Q of D prime, because these are vectors. They're not scalar quantities anymore. And again, I look at what's the worst pair of D and D prime. Hopefully you can compute that in closed form. For instance, if the vectors that I'm trying to compute their average are gradients, and let's say I have clipped norms for those gradients, then the max this thing can change is by the maximum norm of those gradients. As long as you're clipping the norms of the gradients, you're bounding the influence of a user. And same thing, you set the sigma to be sensitivity divided by epsilon. The sensitivity is a scalar quantity. It's not a d-dimensional quantity. It's a norm. A norm is a scalar. And the epsilon is a scalar quantity. And again, we're going to use IID Gaussian noise. Now, what I want you to know is there are good queries and there are bad queries. What are the good queries? The good queries are the queries that have low sensitivity. Because low sensitivity means we can achieve an epsilon at small sigma. We don't have to add a lot of noise. Sigma is proportional to sensitivity. We want sensitivity to be as low as possible. These are the good queries, where one user cannot influence the output of the queries a lot. Here's an example, a made-up example of a good query. If I ask, what are the number of people between ages 0 and 4, 5 and 9, 10 and 14, so on and so forth, this is a multidimensional answer. But each user can only influence one of the ranges. So even though it's a d-dimensional query, you can be in one entry but not the others. So it's like a one-hot, if you've seen that terminology. It's like you put your data in only one bucket but not in all the others. So the sensitivity of this query is only using the L2 norm root 2, because if I swap Peter for somebody else, for Alice, let's say when I go from D to D prime, at most the age group is going to change from one bucket to the other. So in L2 norm, this is going to go up by root 2. The worst case sensitivity of this query is constant in the dimensions. It doesn't grow with the dimension of that query. But imagine I have another type of query. These are the nasty queries. These are the hard ones to handle, where I ask different questions. How many females? What's the number of children? What's the number of people with COVID-19? So on and so forth. If I change one person by another person, that new person can influence, can flip all the counts on all these questions. So you can end up in a situation where by just going from one individual to the other, you influence all the dimensions of this vector. And you can do a little bit of math, it's actually one line, but you can prove that the sensitivity of this query is root t. So it grows with the dimensionality. Now granted, it doesn't grow linearly, but still it grows with the dimensionality. So now I have to add a factor of root d more noise to get to the same epsilon. So this thing can be privatized a lot more easily than the thing above. And that's quite important.
So you need to know in advance what queries you're going to.
Right, and in deep learning, we know those queries. I'll tell you in a bit. Those queries are essentially, we're computing gradients, and we're going to compute the average gradient to do a stochastic gradient descent step. So it's a mean query of d-dimensional vectors that have bounded L2 norm. So it's easy. We're lucky because the queries that we compute in deep learning, when we fine-tune or pre-train with differential privacy, they're all simple queries. But yes, you need to know the query in advance so that you apply DP to it. Okay, again, if you're lost a little bit in the details, totally fine. It's not super important. In a bit, I'll get out of this whole thing. But let's make it a little more interesting. Why is differential privacy so interesting? Obviously, I told you it gives us an operational bound on the performance of the worst-case adversary. I showed you those beautiful figures. Sure, but it has very, very good properties. And hopefully, the math people in the crowd will enjoy these properties. The first property is called the post-processing property, where if we take something that has been DP-fied, so if I take a query, I already applied DP to it, and I can prove to you that it achieves a certain level of DP, epsilon delta DP, you can take it and post-process it however you want, as long as you don't go back and touch the data, of course. But any post-processing function applied to it will preserve the privacy property. So privacy cannot somehow magically degrade. It can only improve by post-processing, but it doesn't degrade. And we can show this formally. That's the first property. The second property is this thing called composition, which I worked on a lot in my early days of PhD. And it turns out to be extremely important for deep learning, which is we're not going to compute one query on the data set. If I'm training a model, I'm doing t iterations of training. I'm touching that data set t times. When we run stochastic gradient descent, we don't do only one update to the model. We do t updates. And these days, we do hundreds of thousands of training rounds or steps. And so if each one of them is privatized, how do we measure the privacy leakage of the combo of 100,000 of them? We need tools that help us track how the privacy is evolving, how those epsilon and delta parameters are evolving. The more I access the data set, the more I'm leaking about it. So we need tools to understand the total combination of leakage. We call this composition. How do these mechanisms compose? Now, there's a lot of math. This thing ended up being the mathiest part of DP in many ways, but it's also so interesting, and there's a lot of machinery. We brought in Renyi divergences and zero concentrated type, all interesting stuff to analyze them. But the TLDR, the takeaway message here is that there's a good way of tracking the overall epsilon after years and years of research. And I'm not going to go into the technical details of it, but again, please take my word for it, that we can track the total privacy epsilon parameter once you access the data set many times. This is one that I was asked explicitly about in the first lecture, which is if something belongs to a few individuals, I think you asked it, it should still be private. If I and, let's say, my siblings, or I and my partner, whatever, we have a certain property, just because it appears in a very small group of people, it doesn't make it something that the model should learn it. And indeed, differential privacy tells us that if there's a property that belongs to one user, so if you go from D to D prime, you only change one user, then if you end up changing K records instead of one, where K is small, you still get a provable guarantee. A weaker, but still provable guarantee. And we know exactly how that guarantee behaves. Again, we have math behind all these things. I'm trying to give you the watered down version of them, but we can quantify precisely for a group of users, let's say a group of 4, a group of 6, a group of 8. We know exactly that. If you train up to epsilon, if it's a group of 4, there's no way the leakage can be more than 4 times epsilon. So the epsilon will grow by a factor of 4, but no more than that. So let's say you were achieving epsilon equals 0.1. If you have a group of 4 users, it would be at most 0.4. So that's important. That means this metric is well behaved. And this last one is the trickiest one of them all. But it's one that ended up also being super important for deep learning. And we have to deal with it. I'll show you how in a bit. It's called privacy amplification by subsampling, which is the following. Intuitively, what it means is that if instead of applying your query on the entire data set, if what you do is you subsample records randomly from the data set, and you apply the query on a subset of those records, on a random subset of those records, that step in itself and of itself has randomness in it. Because now the adversary not only has to fight the noise that you're adding, but it has to also fight the randomness in knowing which records were sampled from the data set. So there are 2 sources of randomness. There's the randomness of which records I've sampled, and there's the randomness of the noise that I've added. And suddenly that randomness from sampling boosts your privacy. It gives you a gain in the privacy. And we know how to quantify that gain for specific sampling schema. So if that sampling is uniformly at random, we know how to analyze the boost. I'm not going to go into the technical details, but assume, for instance, in a deep learning algorithm, in every batch, you're not going to train on all the examples of the dataset. The dataset has hundreds of millions of records. We're by no way going to have a billion or a million or 100 million batch size. We're going to have a batch size of 100, 1,000 maybe, 10,000, but that's it. We don't have compute to have a super duper large batch. So what we're going to do is we're going to sample records and compute the gradient on a random batch. And what this tells us is that you can benefit from that sampling. You can leverage that sampling to boost your privacy. And intuitively, it makes sense because the adversary would have to guess, did Peter actually appear in round 2 of training or round 5 of training? There's randomness in that. We have to hide that information, of course, from the adversary. We shouldn't tell the adversary who was sampled in which round. Okay? So again, all of these are hand-wavy properties. We can put math on them, and we can make them concrete. So I want you to just understand the intuition. That's it.
On the intuition of that last point, is that to say that there is a bit of additional security in the bigger your data gets?
Yes, that's true. Okay. If you're not very sure, it's okay. Let's switch back to something easy. Here's how we apply DP in deep learning. From now on, no equations, no nothing. It's just very operational. Okay. There are 3 or 4 steps. The first step is we take the data set and we randomly sample training examples from it. I'm going to assume I can do uniform sampling. But for now, I'm going to train with, there's no notion of users. There's just examples. So I'm going to call it example level differential privacy. Unlike before where I had users. I'll get to users in a bit. So I'll sample records uniformly at random. This is my batch. I'll compute the gradients, and I'll clip those gradients to a norm S. Why is this clipping step so important? Because it limits the influence any example can make to that query that I'm computing. I have to limit the L2 norm of that gradient. So a priori, I have to fix an S, it's a scalar, that dictates the largest L2 norm any gradient can have. And there's a way to fix it. I'll talk about it in a bit. Okay, so clip the gradient to norm S, L2 norm S, average those clipped gradients, add the Gaussian noise. So you get now a noised average gradient, use it to update the model, and iterate. So if you look at this, it looks a lot like stochastic gradient descent, but there are 2 changes to stochastic gradient descent. In stochastic gradient descent, we don't do the clipping, so we have to add the clipping. To bound the influence of a record, we don't add Gaussian noise in stochastic gradient descent. Otherwise, it's pretty much the same as stochastic gradient descent. If you've seen SGD, that's like SGD with these 2 modifications. So it's very simple. So there's a lot of math, there's a lot of machinery, but in practice, it's actually quite simple. Now, how you compute the epsilon of this thing, that is difficult.
Why Gaussian noise?
That's a very good question. So the community has studied all sorts of noise mechanisms. Turns out that Gaussian isn't necessarily optimal, but it's the one that is most tractable, not just for sampling, for efficiency, sampling efficiency at runtime and scalability, but also when you do this composition, when you try to analyze this specific way of achieving DP across many, many iterations, it turns out to be the easiest one to analyze in as tightly of a fashion as possible. So you could have used Laplace, you could have used, there's all sorts of exotic noises that you could have used. I've myself worked on some of those distributions. There's like something called staircase mechanism that ends up being optimal in some regime. But those are hard to use in machine learning pipeline. So you want something that you have access to easily, you can sample from reliably. Ideally, it has to be a cryptographically secure source of noise for those cryptographers of you, for a reason. Because everything here is just like, I'm speaking, I can sample from a clean Gaussian, I can give you the result theoretically, but in practice, you have some representation via some finite bits, so you have to worry about all sorts of precision issues. I'm not going to go into those details, but there are headaches, essentially.
And is that good for privacy or for computation?
Both. Gaussian ends up being good for both. Okay. Wow.
Since you're clipping the gradients, it means that it's no more, it's biased, right?
Yes, clipping introduces bias.
Yes, and then you're also adding Gaussian noise, which means you're adding variance.
Variance. We're increasing the,
Yeah. These 2 factors, how does it impact the convergence?
That's a very good question. So if I didn't have any bias, so say I choose this clip norm large enough, such that I don't touch the gradients at all, then we know how to analyze stochastic gradient descent, because it's a noisy gradient, at least for convex smooth losses. Now we have a noisier version of SGD, So the sigma is now larger, and so it just slows down the training, but you're still going to converge. Now if you introduce bias, in theory at least, you should not be able to converge to the right optimal minimum in convex smooth losses. And the more biased you are, the more away you are from the optimal minimum. But for deep learning, it tends to work. So this is one of those things where you can analyze it to death in theory, and then you apply it and it works. Okay, just in the interest of time, we have to repeat this many, many iterations until we get convergence similar to any deep learning algorithm. If we want to switch from examples to users, what I've done here is I've sampled users instead of examples. Each user can have multiple examples. Think of this 39 magic number before. And what you do is you apply the gradients on the user, and then you average those gradients, and then you clip the average gradient. So what I'm clipping here is the per user gradient rather than the individual gradients of the user. So that matters. Everything else stays the same. This is now user-level differential privacy. That's the only difference. Okay, so very simple generalization. How do we set that clip norm? If we set it too small, then we can add very little noise, but we cause a lot of bias. If all these gradients are now clipped, there's a lot of bias in the process. If we set it to be very large, we get no clipping. All these gradients would fit in that sphere, but we have to add so much noise because the clip norm dictates the sensitivity. So there's a bias variance trade-off. It turns out there's a process that you can use in real time during training to adapt the norm that you're using to a percentile of the gradient norms that you've seen so far in training. I'm not going to get into it, but there's a very clean approach by my colleagues at Google that we use in production that automatically figures out and sets that clip norm. And you have to do it in a differentially private way, otherwise you violate privacy. So there are some details, but there's a way to calibrate this bias variance to make sure you don't add too much noise, at the same time you don't clip too aggressively. You have to calibrate these two components. I want to go back to that experiment that I was talking about before differential privacy, that Gemini model. We redid all the tests that I told you about, including the membership tests with canaries. Turns out that you can drive reconstruction rates to zero, literally to zero, under DP, and all edit distances, even an edit distance of 5, reconstruction rate 0. And to answer the question, why 39? We wanted to target epsilon equals 10. And for that, we needed to bound things to 39. So there's some math under the hood that was necessary to get 39. So that's why I needed to use 39. So it's fascinating. This is a proof that everything I showed you suddenly disappears when you use DP. Let me show you something else. Remember these two bars that I showed you? Let's do DP now. Epsilon equals 10, 39 repetitions. What happens to the attack that I demonstrated? The true positive rate goes down to 0.1 at a low false positive rate. This is one of the biggest attestations to this technique working. It's not just theoretically it gives you a guarantee, and it's grounded in real math and provable guarantees. You can test it. You can run the same exact attacks that I talked about in the first half of this talk. You can see the tremendous reduction from 100% to 0.1%. So that's the beauty of it. You might wonder if you've seen the y-axis here, there's this thing called empirical epsilons. That is the thing I'm going to talk about in the third lecture. How do we get an empirical epsilon? So I think I'll stop here because the next section is long. Okay, thank you. Thanks a lot. Time for some questions.
Thank you for that. Earlier on, you kind of went, don't worry too much about the details and this and that, and which I thought was interesting choice.
Yeah.
But I'm aware that lots of people who are interested in, say, using federated learning in various data settings, like secure data environment and stuff, they are scared of the details, but also want guarantees like the stuff that DP
Yep.
provides.
Yep.
So I wonder if you had any thoughts on like an effective way to communicate those details without necessarily glossing over stuff.
Yeah, so that's a great question. So first of all, the combo of federated learning and differential privacy is what I'm going to cover in the third lecture. And I think it's very interesting in its own way because it's going to create a lot of challenges that we're going to have to resolve. So hopefully you can be there for that talk. Second, for the other part of your question about people want to use this, maybe they're not privacy experts, they don't want to know the details. So what we need is open source code that's high quality, that's written by professionals, that's audited by experts. It's in the open, so everybody can vet the code, can tell you whether or not it's doing what it's supposed to do. It's adding the right nodes at the right place, it's end-to-end tested, regression tested, so on and so forth. That engineers who are not experts, they can actually listen to the key opinion formers and experts in the community and be like, okay, this is vetted, I can use it. And you need simple APIs such that you can just import blah from blah and then just put it into your training process. We've worked towards that. We have a library called JAX Privacy. It uses JAX training under the hood. PyTorch has a library also, if you prefer PyTorch, it's called Opacus, that implements differential privacy for deep learning training. So all these modern ML frameworks have implementations of differential privacy. It's still hard to use because there are parameters that you have to adjust, like the clip norm, the sensitivity, how many training examples, I used this weird 39 number. There's things that you still have to control, but it makes it a lot easier for engineers to use it. And the communication part, we're trying to write simple blog posts that distill and simplify the exposition. You can see that what I've done here in the first two lectures is I've taken something that's very highly mathematical. I've tried to tailor it to an audience that may not be as interested in privacy or as knowledgeable about privacy research. So there are ways in which you can explain these things to everybody, hopefully.
So you're writing some noise during the steps that will sort of change the results of the output strings, right? So how would that affect a regular user trying to use it legitimately? Would you expect some more errors?
Yes, so that's a very good question. There are people who have studied the impact of differential privacy on those outlier users. So obviously, DP will treat outlier users as sensitive individuals, right? And they would try to make sure the model does not memorize information from those users because it's trying to protect their privacy. It doesn't want to leak their information. But that naturally means that the model will start working less well for those people. So if I tend to align more with the average user, I'm very typical in many ways, then I'll use the model and I'll enjoy it. But if I'm a user who doesn't subscribe to the average individual user in the data set, then it's going to be less good for me. Now, hopefully, there's still a lot that will work for me, like the language will still work largely, so on and so forth. But you need to personalize. So that brings me to the third and last step of this, where we don't just train on user data. We don't just fine-tune these large models on user data. We personalize to each individual interests and preferences. So we need personalization. DP alone will not work right out of the box. You need to take that model, broadcast it, personalize it, and that's an open question. There's some work that's been done, but it's still largely unsolved.
So in DP, you're clipping the gradients to, I think I understand, so to limit how much the model can change as a result of this one country, the average.
Yeah.
We're doing that on the gradients, but obviously those are just like on parameters of this kind of black box model. If hypothetically you could do that sort of same process on the actual outputs of the model, so say the predictions it actually gives, if you could clip those, so I only want to change the prediction by like one unit or so. Would you do that instead? Is the kind of clipping of the gradient just kind of a proxy for that?
So the reason why we clip the gradients is because we want to control the sensitivity of the query. And I cannot, by just limiting through directly processing the text or the data, limit the influence of that user's there's like a nonlinear transformation from data to gradients. Because I don't have that ability to do it properly on the data, what I do is I just go and make an intervention at the gradient level. That's the easiest, cleanest way to bound the influence. And it turns out, I mean, I don't know if folks in this crowd have fine-tuned LLMs or looked at their training. It turns out that clipping is actually necessary for the convergence of models. So even if you don't care about DP altogether, if you've seen LLM training, clipping, and there's a clipping profile, is actually important. It turns out. So this is something that again, in theory, it's hard to justify. Why are we introducing this bias? In practice, it turns out to actually take you to the right basin, where a good local optimum lives.
Okay, one last question.
So we've seen examples that you show with textual data. Have you seen DP being applied to like other modalities like images and?
Yes, vision, text, and speech, all three. I haven't seen video, but I've seen vision, text, and speech. All the same underpinnings apply. And this talk I'm focusing on text because language models, but you can do it for vision, you can do it for speech. And you can do it using diffusion models, transformers, combo of transformers, diffusion. The same, everything I talked about would apply.